not much we know, right, about new processors, so we can explore all possible behaviors or most of the possible behaviors of the process using simulators. But before we can create the simulator, we need to first develop the model for that particular process. So roughly, I'm going to talk about the introduction to chemical looping hydrogen production as a motivation. And then we look at the illustration, how we view this process. So we can view it, divide the process into three compartments: pellet solid, pellet void, and bulk reactor compartments. Again, this is depend on the modeler. Process modeling is not exactly a science because you also need a creativity. You need to be creative when we develop a model. Okay, we need to be a creative. So we cannot really follow an exact science here. We mix science with a bit of creativities. And then we look at the scheme, how this grain can be converted from one type to another. And then we start to do the modeling for this pellet solid compartment. And then we look at the reaction kinetics that we can use. Then also we move on to modeling the pellet void compartment and then bulk reactor compartment. Okay, once we have all the equation that we need, then we can start developing our MATLAB simulator. Okay, let us begin with this one first as an introduction. So what is chemical looping hydrogen production? So this is just an illustration, a process where we can produce hydrogen. So here we have three reactors. We can have two reactors as well, but in this configuration, we have three reactors, namely reducer. This is the reducer. Okay, we're going to model this reducer later on. And then the second one is oxidizer. The third one we call combustor. Essentially, what we're trying to do is that we have what they call oxygen carrier, OC. Let's say we use iron oxide. We can use other type of oxygen carrier as well, like nickel oxide, copper oxide, and many others. But here, the most common one, widely studied now, is the iron oxide. Okay, and the other one is nickel oxide. So I use here the iron oxide as a case study. So this one carrying oxygen. So what we need here, we need a reducing gas. So this gas actually will reduce this iron oxide, right? This is hematite. It will be reduced to magnetite, Fe3O4, and I think to FeO as well, but a little bit to Fe. Okay, mostly actually a mixture of Fe3O4 and FeO with a tiny amount of Fe. So now this reduced oxide will be sent to oxidizer. So what we feed to the oxidizer is actually steam. Okay, so the steam will react with this reduced oxide and then produce hydrogen. So here we have hydrogen as well as water. So again, water can be separated from hydrogen by condensation. Similarly, also here, basically, we have also a product, in this case, H2O and CO2. So how can we separate CO2 from water? We can just use condensation to do that. So it's much cheaper in this way, anyway, in terms of separation of the gas. So now what happened is that this oxygen carrier basically partially oxidized, not all of them all the way to Fe2 or 3, mostly up to Fe3 or 4, a little, I think some amount of Fe2 or 3, depending on the length of this reactor, how you configure it. Actually, once we have a simulator, we can develop a different configuration for this reactor. Okay. So now what we do is that we're going to burn this oxide so that we can recover it back all the way to Fe2O3, then recycle it back. So this is a moving bed reactor. Okay, there are three modes that we can use: a fixed bed, moving bed, and the other one is a fluidized bed. Okay, a moving bed is actually a good candidate because it can produce high productivity of hydrogen. Here we can have a carbon capture, easy carbon capture, because we can separate CO2 easily from H2O. So normally we can design, our design objective can be consist of these three things. H2 production together with CO2 capture and also power generation, because these two reactor produce a lot of heat, and that heat can be used in the boiler to produce steam. And steam can be used to generate electricity. Okay, that's more or less the introduction for chemical looping hydrogen production. So now we have a oxygen carrier. This one we call oxygen carrier. Okay, it's a pellet. So our pellet here is iron oxide. Okay, so we have a casing inside the reactor pipe. So basically, we have a pipe there, maybe 5 centimeter or 7 centimeters, depending on the designer. Okay, the size of that pipe. So this pellet could be 1 centimeter or less than that, depending again on the designer. Now in between here we have bulk gas. Okay. Now also we can have cooling or heating medium in the outside here. Sometimes we can use a cooling medium if the net reaction is isothermic. If the net reaction is endothermic, we can use if it's endothermic, we can use a heating medium. So this is oxygen carrier moving downward, say, and then you have a reducing gas counter current to that oxygen carrier. Then also we can have a cooling medium or heating medium, depending on the reactor, whether it's net isothermic or endothermic. So overall configuration normally is multi-tubular reactor. Okay, we have many pipes there, few thousand, maybe a few hundred of pipes, depending on the designer again. So the pellet will flow in the pipe, and the cooling or heating medium is outside the pipe in the shell side. Again, this is not an example. There's a specific design here. How do you actually fit this pellet into the pipe? We're not going to talk about that. We're going to look at the model only, okay, not at the engineering design of that heat. There's a specific design for that one. So what we see here, this okay. So this is the view for only one pipe. We take one pipe here, and then we can see this view. Now we look at further into one oxygen carrier pellet. So imagine that the pellet is actually spherical in shape. So this is the pellet. Inside the pellet, we have this is normally a porous pellet, so that it allows gas to diffuse into the pellet. So the reaction actually occurring inside the pellet, not outside. So you can view also inside the pellet, we have tiny grain, you call it. So this grain can be of different type. It could be iron or magnetite, or could be hematite. This one is, let's say, it could be hematite. Okay, the blue one could be magnetite. This purple one uh, could be FeO. Okay, different type of grain inside this pellet. So the reactant gas, for example, if we use in gas, the reactant gas could be CO and H2, or we can just have a CO. In this case, we just look at one reactant gas only, which is CO. So that's supposed to diffuse into the pellet. And then, of course, it will produce a product gas, like if we use a CO, the product gas is CO2 that will diffuse out into the bulk reactor. Okay. All right. Now we have seen the pellet. Okay, let's imagine again we have a pellet. Inside the pellet, we have many grains, and we can have a different type of grain. We can have Fe2O3, we can have Fe3O4, or we can have a FeO, or also actually in practice we can have iron, metallic iron as well. But here we just stop up to FeO. Okay, just to simplify the presentations here. All right, so now we can imagine that this pellet consists of Fe2O3, that's a hematite, okay, magnetite, and wustite. Okay, FeO is wustite. So this one we can categorize as a solid compartment. So yeah, this one I put it on the top here, I think. Okay, so this is a solid compartment. And next to it, because the pellet is porous, okay, we have okay, void compartment or case phase compartment. Okay, so we have two compartments already, right? So the next one is actually the bar reactor compartment, right? Reaction. Okay, first before we move on to the next one, so we just look at first at the type of reaction that can occur for a particular grain. Now imagine now we have a grain that start with Fe2O3. This is a tiny grain here within a pellet. So it will react with CO, the reducing gas, and of course it will produce CO2. So we expect this one will be converted, okay, directly to Fe3O4. Okay, and again, this one still can react with CO, produce CO2. It will be reduced further to FeO. And again, in theory, FeO still can react with CO, produce CO2. Then, of course, it goes to metallic grade. But again, I don't want to go all the way to that point because most of the reaction practically it will stop at FeO with a little bit of reaction further forward. Okay. Because in order to reduce this further, we need high concentration of CO. Okay. So actually, if you want a high conversion of CO, right, this concentration will be low already. So if this concentration is low, that's the reason why we cannot really push this reaction forward further to Fe. Okay. So this reaction is a reversible reaction. So we have a oxygen carrier here, Fe2O3, react with CO that produce the Fe3O4, produce CO2. Okay, from the second stage, we have Fe3O4 react with CO that will produce FeO plus CO2. All right, everything is simple enough. Assumption, fast reaction compared to bulk reactor in dynamic. And of course, we have a tiny grain. The other one is shrinking core. This one is more complicated. Okay, so we start first, let's say we Fe2O3, react again as before with CO, produce CO2. So it will not be converted. Again, the reaction is still the same. Okay. However, in this case, the core here start to shrink. Right? As you can see, that this grain size start to be reduced. Fe2O3. Now outside that we have the other grain, which is Fe3O4. Again, it still can react with CO and CO2. Then, as you can see now, we can see the core is reduced further. Fe2 is smaller now. Now we have another layer outside, which is FeO, because Fe3O4 will be consumed, right, through a reaction to produce FeO. Again, this one take longer time, and eventually all of this will be converted to one particular grain, let's say all the way to FeO. Could be a mixture of FeO, and Fe3O4. So this one is shrinking core scheme for the grain. Assumption, when the reaction is relatively slow, and of course, we are dealing with large grain. Okay, now we look at the oxygen carrier solid compartment model. We look at a pellet, yeah, okay, we focus on one particular pellet, not yet the entire reactor. So we have this reaction, and this reaction is reversible. We have forward reaction, and as well, we have a backward reaction. Okay, same thing for the second reaction, we have forward and as well as a backward reaction. So let's say we conduct a mole balance for the first grain, which is Fe2O3. Okay, we conduct the mole balance for that. So Ng here, meaning to say the mole of grain. So I indicate 1 for Fe2O3. So if we look at this reaction, right, they will move to the other side. So this one is consumed. So we have 3 of this. Okay, we have stoichiometry. Coefficient for this is 3, so that is -3 because it consumed by forward reaction. Also, this one appear to be consumed by backward reaction, but later actually backward reaction here is a negative. So basically negative, they will produce back this one, right? Fe2O3 is supposed to be plus here. However, I just maintain a negative one because I allow this RB1 to be negative. Okay, because negative and negative, this actually become positive, and actually this one will produce back Fe2O3. Okay. So this is notation. Again, there's a note for this. So I will not read the notation because I just want to reduce the time for that presentation. So I just focus on the main one. So forward reaction here must be positive, and backward reaction here supposed to be negative. Okay, so there's a sign for that. Okay, next one we move on to the second main Fe3O4. Again, we just refer back to the scheme here. So we produce the Fe3O4 through the first reaction, and of course we consume that through the second reaction. So this is the first reaction, right? That's consumed. Again, for the RB here, it's supposed to be negative if we have a backward reaction. So this will be minus here. So basically minus, this one will be consumed back, right? To produce Fe2O3. And then the second reaction here is minus from this one, RF2. Then you could also go back there, okay? So that can produce Fe3O4. So again, here is negative. Is negative meaning to say that one will be produced back because this one negative, negative will become positive. Again, that is just a convention for convenient one. Forward reaction, again, the same thing before, RF2 is positive and RB2, the sign for that is negative. Now, finally, we move on to the third species for that grain, which is FeO. Again, we write it as before. This time we got 3 because only reaction 2 that produce FeO. So that's why we have reaction 2, RF2 and RB2. So the stoichiometry for that is 3. Yeah. So we'll multiply with 3. Yeah. Again, this is for a pellet. Later we modify it again. Okay. All right. Total grain surface area in a pellet. So basically, we imagine that we have a lot of pellets. In the pellets, we have a grain, many grains there. So here we are interested to calculate the total grain surface area in a pellet. Okay, just in a pellet. So now let's say surface area of a grain of any type. Any type could be Fe2 or 3 or could be FeO. So that is 4 pi because we assume the grain shape is spherical. So that is 4 pi Rg square. Rg here is the grain radius. We assume in this case the radius of the grain is constant or fixed. But in practice, again, it could change depending on the type of the grain. But here we just deal with a simple case first. Let's say we assume this one is constant. Then also we can have a volume for the grain that is for over 3 pi Rg cubed. Now, actually, we can calculate the total surface area of grains of any type in a pellet is actually given by this one. Sg equal to Ng. Ng is the mole of that grain, the number of mole of that grain inside the pellet. A molecular weight of that grain over Rg multiplied by the density of that grain. So for the density of Fe2O3, that is around, again, these are from the open literature. So I just take the average one, which is around 5.14 times 10 to the power 6 gram per meter cube. So Fe3O4 is about 5.2. FeO is about 5.7 times 10 to the power 6 gram per meter cube. So also we can use the molecular weight again. The molecular weight for Fe2O3 is 159.69. So we need a molecular weight for all of that grains. We use that later in this calculation. All right. So Rg grain radius, NOG here, there is a number of grain of any type in a pellet. Okay, you can have 3 different type of pellet, grains type, right, in the pellet. So it could be any one of that. Now we look at reaction kinetic. This is the important one. So again, we look at the reaction as a reference here. This is the reaction, reversible reaction. So this is the reversible reaction. Equation is given by this one. This is the kinetic parameter. C1 here is for because we are dealing with the CO only. Okay, CO2 mixture. Okay, our reducing gas is CO, carbon monoxide. So the product of that CO2. So C1 here is carbon monoxide concentration. C2 is the carbon dioxide concentration. Km1 here is the equilibrium constant. So therefore, you can see this reaction could be negative or positive. Okay, this is notation. So if R1 here is positive, right? So we need to say the reaction is, we have a forward reaction. So we just negate RF1 equal to R1. And of course, the backward reaction is 0. It cannot be both exist anyway. It could be either one of it. So, however, if R1 is negative, we need to say this term, right? This term is more dominant than this one. So RF1 here is 0 and RB1 become R1. Okay. So that is an important one. So we look at this thing again. I think I will explain later on when I move forward to the next slide. Yeah. So same thing also for R2. Okay. So void compartment model. So we look at a pellet again. This is still inside a pellet. So we have a pellet, and then we have a lot of grain inside there, and then we have a void or empty space. So we want to model the concentration of gases inside that empty space. So we can imagine that we have this one already. I already explained to you this part, the modeling for this one. This is the solid part. This one is the void part. This is what I'm going to do now. Again, the same reaction. Now we're dealing with a gas rather than with a solid. Yeah. So mole balance for CO, the reactant gas. Okay, so CP1 here is the concentration of CO inside this pellet. So now, what happened here, we have the VPAP. So this is the volume of the space inside this pellet. Okay, we assume the volume of that space or empty space is constant, does not change throughout the reaction. It might change, but I think the simplest case, we assume that these are constant. J1 here is a diffusion, right? J1 is a diffusion of the CO gas from the bulk phase into the pellet. So again, this J1 is depend on is per pellet. Okay, per pellet, so there has to be multiplied with the surface area of the pellet, AP here. Again, I will explain that further a little bit more. So now this is the reaction that consume the CO. SG1 here is based on the grain number 1. But if the backward reaction occur, that has to be based on the Fe3O4, because without Fe3O4, this one will not occur. Okay, for the backward reaction to occur, remember that this Fe3O4 must exist. I haven't explained it yet. So that's why we multiply this with Sg2, meaning to say the surface area for Fe3O4 grain. Sg1 is the surface area for the Fe2O3 grain. So if forward is based on this one, it's a backward based on this one. Now, again, CO is still consumed by the second reaction. This one we consume CO as well. So again, for the forward, that is based on Sg2, meaning to say if this exists, then you can have a forward reaction. Otherwise, you cannot have a forward reaction there. Or same thing also, if backward reaction occur, it has to be based on FeO. Because without FeO, right, that you cannot have a backward reaction for this second reaction. So that's why this one is different. Okay, I haven't, hopefully I will explain that one. It's quite important. Now, the next one also for the mole balance for CO2, there is a product one. So we have a diffusion again, in out from the bulk phase. So we just indicate as J2. J2 here is the diffusion flux. Okay, AB is the surface area of the pellet. Okay, that's a notation. Now, finally, we look at the gas diffusion flux in out of a pellet. How we define that? Again, we assume we have a pellet. It's a porous pellet. Okay, inside the pellet, we have a concentration of the gas, CPI. I here could be for CO or CO2. Okay. Now, again, as we know that outside this pellet, we have a tiny, a thin film. Okay, we have thin film there or gas film. So normally we call that could be a laminar layer with certain thickness delta X. So now the bulk gas concentration as CBI, I here could represent CO or CO2. So, so we can multiply this on the flux of any gas from the bulk phase to the pellet. So that is given by the bulk concentration minus the CPI, the concentration inside this pellet. If that is greater than zero, of course, the gas will diffuse into the pellet. If that is negative, meaning to say the gas diffuse out of the pellet. Okay. So normally we define diffusion as DI, this is diffusion coefficient, multiplied with the concentration gradient. Again, delta X, we don't know that, so we can lump them together as DAI. So basically, if we don't know how to, the exact value for DAI, we can actually look at the literatures, or there's a certain method, how can we calculate this one? Okay, but I will not include this here for in this workshop. We don't have enough time for that. So what we can do, we can play around with DAI here to see the diffusion effects on the overall reaction. We can use this one as our what they call control parameters, not to play around. Again, this JI gas diffusion molar flux in out of a pellet. So this one mole per meter square per second. Okay, there's I missed a second there, I think in the note, so you can write it down. Mole per meter square per second. Again, actually, this is per pellet, okay, because this is only defined for one pellet only. So if you want to get the overall diffusion flux, we have to multiply that with the number of pellets. That's what I will show you later on. Yeah. Okay. Now, conceptual framework of reactor pellet grain model. We have three components. One is bulk reactor. The other one is a pellet void, and also we have a grain one, right? The grain one represents a pellet solid one. Okay, so now imagine this is your reactor. Again, we just look at this everything here. We lump all the pipe together as a single reactor like this one. Okay, inside the reactor, we have a pellet and a gas flowing inside there. And outside here, you can have a cooling medium or heating medium. So this is a part, so this reactor could be quite long, could be a few meters long. So what we do is that we're going to divide it into section. Okay, let's say each section, the length of that is delta L. Okay, so consider now one section here. Now we can lump together all of the pellet solid inside the section. So this one for the entire particle or for the entire pellets. So we just lump them together into a single zone. We call it pellet solid zone or pellet solid compartment. So we can have lump all the empty space inside the pellet, combined together. We call it pellet void compartment. And the remaining part outside this pellet, we have a bulk reactor. Okay, so we have three compartments now. So this with delta N, this is the length of the section. So imagine now we have feed gas, could be a mixture of CO and CO2, right? So we have an initial concentration or inlet concentration, CB1I, CB2I. We have the temperature for that, TBI. We have the flow rate for that gas. So that gas will flow to the bulk reactor. Okay, it will not flow inside here. Okay, because this is solid, this part. So this one is the passage that they can go through. So the bulk reactors. So that will be out. Okay, just call it CB1, CB2, TB, FTO. O indicate the outlet one. How about the pellet? The pellet will go to this part. Okay. So now we have pellet flow, we call it MTF, right? So we have initial mole for the grain, the inlet mole for grain one, the inlet mole for grain number two. Grain number two is Fe3O4, and so on. Then we can have also inside the pellet, okay, but inside the void here, we have a concentration of CO and CO2. We indicate it as CP1 and CP2. Then the pellet can have a different temperature from the bulk gas, so we indicate it as a TP. Outlet. So again, we assume that the rate of pellet that go into the reactor will be the same as the rate of pellet leaving the reactor. Okay, this one is constant here. unless there's some destruction, maybe one or two that pellet being destroyed, right, during the process. Again, that could happen in practice, but in this case, we just look at the theoretical aspect of it first. Okay, none of it being destroyed. So if 10's coming in, 10's will leave the reactor. So the same rate. So this is for the whole pellet zone. So here we divide reactor into several sections. Now we can apply line parameter modeling for each section. Okay, this is the notation that I use. Okay, there's a gas diffusion here, right, between bulk reactor and the pellet void, in out of the gas diffusion. So let us take a look at the pellet solid compartment. Okay, we look at this one first, yeah. So we have the previous equation. Okay, this is the previous equation that we have. So now what we do is that we're going to add the moving part of it, which is NPF. So this is the rate of flow of the pellet in terms of the number of pellets per second that flows into the reactor and also leaving the reactor. So that is NPF, rate of flow of the pellet. So each of the pellet, again, you can bring new green, NG1. So that is for the hematite one. There's I to indicate the inlet here. NG1 is the outlet mode of that grade number one. Again, since we use a lamp parameter model, okay, so we assume CSTR complete missing inside here. So the concentration of the mole inside here should be the same as the concentration of mole leaving that particular system. Yeah. So we can actually, this NOP here is the number of pellet because this is for the one pellet only. So the mole here, right? The mole of grain here is only for one pellet. So in order to get the total amount of mole for that particular grain, we need to multiply it with the total number of pellet inside this section. This is reactor section. So now we can actually simplify it, then we get something like this one. Same thing also for Fe3O4 grain. Okay, same form. This is still the same as before. The only thing now we add this part, the moving part. And finally, also the same for the mole balance for the FeO grain. This is the same as what we derived before. Since we have a moving pellet in and out of the zone, this is a bigger zone, not a one pellet. So we need to add this part. NOP number of OC pellet in the reactor section. Same thing for the pellet void, we use the previous equation. Okay, remember that Cp here is the concentration inside the pellet. So to get the number of mole for one pellet, so we have multiply with this part, right? Now to get the amount of that particular gas inside the zone, okay, so we need to multiply that with the total number of the pellet inside that particular reactor section. So that's why we add this part. So this is again the same as what we had before. The only thing we add the moving part in this section. After that, we can simplify it like this one. Then we can move on to the second species, which is CO2. Again, same as before. Now we just add this part. Okay. Finally, bulk reactor compartment. So for the bulk reactor compartment, we apply mole balance for CO. So there is the rate of change of CO. Okay, CO concentration inside this zone, this bulk reactor zone or bulk reactor compartment. So that is the inlet for the CO from here inlet and then minus the outlet. Okay, minus we assume that the flow of the flux is from the bulk reactor to the pellet void. Okay, so that's why we put minus here. J1 multiplied by AP because J1 is defined for a single pellet. So single pellet multiplied by the surface area of the pellet that give you the flux, the flow rate, right? The flow rate of that CO into that particular pellet. So to get a total one, multiply with the number of pellets inside this reactor section. So we can simplify this further, we get something that look like this. Same thing also for the mole balance of CO2. Okay. Now, how about FGO? How do you calculate FGO? We can calculate FGO knowing that if there's a loss of mass, right, from this bulk reactor, it must be due to the diffusion into the pellet. So this pellet actually carrying some of the mass or some of the gas out here. So actually, if you look at the modeling in some article, I think they don't really consider this one. Okay, the model that I show you here is a different one, quite different approach. I use a different approach from what mainly researchers use in the articles. You can see the different models, okay, that they use or different approach. But after I look at all of that approach, actually I try to simplify and make it more common sense, easy for us to see the things, like to feel it, to have intuition about that model, rather than just look at the math with it and then follow a standard mathematical procedure to solve it. You give to the system boundary condition and the initial value condition, and you solve it. Basically, in that case, you don't really feel what is going on inside that process. So I use this approach because you can feel it. You can visualize what actually happened in the pellets. So that's why I use this approach. So this approach here, actually, in some of the model, they don't really consider the loss of the gas because this pellet actually can carry the gas out. You see, so they don't really consider. In this case, we consider there's a loss of gas because of the pellet carrying the gas out. Okay, so that's the mod. So this FGO is not the same as FGI. Slightly different, could be a lot more different depending on the size of the pellet and the porosity of the pellet, depending on the NPF as well. Okay, so that difference can be quite significant. Okay, so then this is the equation that we have. Okay, we list down all of the ODE equation that we have. Also, we list some of the algebraic equation that we have. This is algebraic equation, but the algebraic equation that we have here are not enough. We still need to we need a few more algebraic equation to do the calculation of pellet density, for example, to calculate the number of grain in the pellet and so on. But again, we can do that later on, in the second part. Okay, this is more or less what we have so far. Not the complete one, but I think we have around 60% of it. So if we have 60%, that's good enough. We need to say we start to have our backbone already. From there, we can grow it up. Because when we tackle a complex system, when we try to model a complex system, we look at the basic thing first, what we can produce from the basic knowledge. Then after that, we keep adding it bit by bit, layer by layer, so that to make it more complicated or more realistic and so on and so forth. Okay, that's all for this part. Okay, that's kind of part one. So let us take a break. If you want to have you want to ask question, you can type in the chat box there. Maybe later I can try to address it. Okay, so type in the chat box. But I think before we move on to the part two, let us take a break first, 10 minutes like that. Yeah, or you can ask question first. It's up to you. Okay, I go back now to the host now. Okay, go back to you to the host. Okay, so what to do next? Yeah. Right.
Okay, doctor.
Okay.
Okay, doctor. Thank you for the part one. We break to 10 minutes. So I will list out the question that maybe appear in the chat box. So to 255, we can start again. Okay, Dr. Jobran.
Okay, can. Sure.
255, we start again. Okay.
Okay, we
We
take a
can
break
take
first,
10
10-minute
minutes.
coffee time.
Okay, good afternoon to the all participants. So, Dr. Jufran, uh, we can start how we take a break a little bit. Now is 2:55 p.m.
Okay, so I try to share first. Uh, so can everybody see this one, the slide? Is it clear, the slide?
Okay, the participation, you can also download the slide in the chat pod. We provided in the links.
Okay. So I just move on, huh? It's okay, yeah? So okay, second question, we're going to play with MATLAB. So please, if you have MATLAB at home or in your laptop, you can okay turn on your MATLAB first. Okay. So I use MATLAB version 2024B. So it doesn't matter. You can use some MATLAB slightly earlier or older than this one. It should be okay. 22 or 23B or A can be used as well. So it doesn't matter because we use a script. The script is actually can be used for different type of MATLAB release. The only thing is that the strict restriction is for the Simulink model. So if we use a Simulink model, let's say we develop a Simulink model using MATLAB 2024B. So if I want to open it using 2020, so I cannot open it. So I can open it only with the latest version or the later version. I can use, let's say, 2025 A or B to open this, but not the older version. But for the script, it's fine. So it should be okay. So open the MATLAB first, and then you can go to, you can create a folder. Yeah, to create a folders. So we move to the any folders there. Then you create a folder name, and then you select that folders. So now my folder is here. This is my folder, script reducer CO. If you want to go to your directory, right, you go to this one, browse this one. Okay, then you create a folder there, and then you just select the folders. Okay, so I already developed that function. So what I'm going to do is that I will let you to write that function as well, and then you test it whether it work or not. Okay. So this is roughly what we have. I have prepared just to make it easy to follow. So here is our MATLAB. You open the MATLAB already by now. So in MATLAB you have a command windows where you can type your command. Let's say 1+1, right? There's a command that comes 2. So you can type here, and then you can see that in the workspace where you will store the information in the workspace. On this side here, you have a current folder. Again, this is the different people might have different layout there, because you can change the layout actually. For me, I just use this layout. Okay. So the first function that I want to write is to calculate the number of moles of a gas given temperature, pressure, and volume of that gas. Okay, we use ideal gas law. So this function is very short. Only how many lines? Only 13 lines here. So this one, what you see here. So this is a command line. So, excuse me. So command line will not be executed. So they just use a note. You need to write some note there on the files, right? So that you know what the function is supposed to do, including the unit and a few other things. So the line here, for example, only line 1, line 7, and line 11 will be executed. Of course, the number 13 as well. This is the end. And here to indicate it's the end of this function. So we develop a separate function like this one. Okay, function number one, mole case. Again, the name of that function is up to you actually. But I just want to create this number one, number two, number three, so that easy for me to to see the sequence of it. If you have so many functions, if you don't, you just simply name it. Basically, it's hard for you to identify that which function that you want to use later on. Okay, let's try this function. So to do that, okay, let's do this for one time. So you go to the script. There's two types of script. One is the live script. The other one is new script. Or you can go to this part here as well. You have a live script, and also the other one is you can use this function. But normally this one to build a script, just a new script only. Okay. Okay. So in this case, so I just use this script. Just click on this one. Okay. Now, if I want to make this one, maybe I just make this very bigger. You can see the what I call this one. I think just wait a minute. So I can go to the preference, right? I go to preference. Let's say you want to increase the size of that font. Custom. Then it's an editor. This one we call editor. The script, we have a script editor where you can type the commands that you want. So maybe I just increase the font size to 14 so that easy for you to see from that side. Okay. Now, what happened here? You have this. Okay, this one is the editor. So you can dock this editor. You can click it here. For example, you can dock it editor to the MATLAB itself. So it will be part of the main MATLAB. This is main MATLAB window here. But suppose you want that editor to stand alone, so you just click on this side and then undock it. Yeah. So in this case, I prefer it to stand alone like this one. Then here to create a function, you start with function first. Name. Okay, function, for example, in this case, right? Okay. Function name, function. Then after that, followed by the name of the variable. Okay, the variable here and guess, right? Number n to indicate the number of mole for the guess. But you can use different name as well, n mole, for example. So here we can start to use n mole, something like that, or whatever you want to call it. And then you can start with a number one. So you cannot use this one here. You need to use underscore, okay, to connect it. Then you start to type a name. So again, I don't want to do it again. So what I want to do is I have to show you what I have written, and then you follow it. Okay, let's see whether you can do it. This part. Okay, this is the what I have created. Okay, function. Okay, let's call that output as n guess. Okay, and then the name of that no number one mole guess. So this one is the input. Okay, this is the input of that function, the one that you want to calculate. This one are the input, meaning to say you need to supply these values in order to calculate the mole of that gas. So this one we call input inside here. So we just write this one. You don't need to write it now, actually. You just follow that the thing. You just write this part here. So this is the line that will be executed. Okay. This one. The one with the percentage meaning to say a command line. So this line will not be executed by MATLAB. So it just as a note. I think in your case, just to save time, you don't need to write the command there. Okay. So after this, anyway, you will have this one. So basically, you can get this slide thing from the host anyway. So you can follow that later on. But for the time being, we just type the one without the command one. Okay. Right? It give you, let's say, 2 minutes to do that. It's very simple. Like that, and after that, you save it. So when you save this one, right, make sure the name of that is the same as the name of the function. So the name of the file is exactly the name is the same name as the name of the function. If it's not the same, this one will be underlined with red one. So meaning to say the file name and the function name are different, right? So you need to make sure the file's name that you save it using file name, which is the same as the name of the function. Therefore, it will avoid clashes in the future. Otherwise, it can clashes with other function. So that is a ideal gas law. Can already know how to do that, I think. So you can use this one to calculate the number of mole for that particular gas when you have specified the value for pressure, temperature, and volume for the gas. Okay, we will use this later. So what we're trying to do actually, we want to write the function that we're going to use in our model later on. We need a number, quite a lot of functions there. Okay, so or something that you want to calculate repeatedly. Basically, you just write it as a function. Now, how to use this function? So basically, let's say we have here, we just copy this one. Okay, so let's say we go to the command. This one is not big enough. I just want to make this command window size bigger. So go to preference. Okay, command window. Make sure this one is slightly bigger. Custom. Okay. Okay, just type it there. But if you want to run that one, right? So basically it's wrong because you haven't supplied the value for P, T, and V. So let us supply the value for P here. Let's say this one equal to 1 bar. 1 bar is 100,000, right? So 100,000, we can type that one E5. Okay. E here means to say multiply by 10 to the power 5. Okay. And then let's say the temperature. For our case, our temperature is quite high. Let's say we use around 800 degrees Celsius. For chemical looping, reducer running around 800 to 900 degrees Celsius. And then you can type V here. Let's say you want to look at the 1 meter cube, for example. 1 meter cube. So how much is that? So now what we can do is that we can just press page up to move back to that one. So that give you, right, that one is 11.2 mole. So the amount of gas is 11.2 mole. Okay. Right. Anybody have any issue with this? So this is using command window, but you can also use the other new what they call use the live script to do this one. So now I have shown you how to use command window to actually call this function. We call this function right in command window. Then from that we can find the amount of mole, the number of mole of gas in our system for the given P, T, and V. I'm going to use a live script there. You can click on the new script, this one here. Click on this. Okay. Now in the new script, I can do the same thing as well. Okay. So let's say you can put P here. Press P. Again, this is a bit small. And I'm not so sure whether I can increase the size of this. Let me see first. I can get the size of that. Command editor. Maybe not. Editor is already. So I think I just use this one. I think hopefully you can see it. Okay, let's say P, we define that as P1E5. There is a 1 bar, right? Or 100 kilopascal. We can type here this one inside of Pascal. The unit is Pascal. Then you have a temperature equal to 800. So put a comment in the back there. Type like this one, insert a comment there so that we know what that is. So this one in terms of degrees Celsius. Okay. Volume. So this one is a 1 meter cube. So this is meter cube. After that, we just call that file again. We just go back to that and paste it here. Paste it there. Then after that, what we can do, we just run this one. Click run here. Uh, so that tells you this, the amount of gas, the number of mole of gas here in the system is 11.2 mole. Okay. Now this one we can save it. So in this one, we can really save this command window. Actually, it makes a lot of things there. So the beauty of the live script is that we can save it. So let's say we save this one, save it as uh, maybe for workshop. Just call it workshop testing, just for testing. Okay. So basically, you can see that in the live script here. If you click on the folders, right, current folder, you can click here. The live script is there. Okay. So next time we still can call it. Now, if you want to change the value, maybe here we want to change this temperature from 800 maybe to 850, right? We can change it like that. This one maybe for reducer, normally we use around, I think maybe a maximum up to 20 bar. 20 bar is about 200, about 20, 20 bar is 20 times 10 to the power 5, right? Let's say 10 bar, we want to increase it up to 10 bar. So that is a star 1E, okay, 10 bar. So you run this one. So basically the amount of the gas is increasing from 11 just now to 107 mole inside this the same volume, which is 1 meter cube. Okay, next with this part. Now what we do is that it's a common practice, right? When we're going to write a lot of function, then it's possible also that function will clash or we forget the use of that function. So what we can do, I suggest that based on the experience. So what you can do is that you can write something, list a function like this one. Okay. So here you write in the Excel, you catalog yourself, you have a list of function and application. Okay, for example, we just developed our first function just now, then you just write down what is the application of that, what type of function, is it algebraic, is it ODE. So again, you can put more remarks there because believe me, when you develop something which is complex, right? For researchers, we actually developing a model which can be very complex there. Then it involve a lot of function. You can have 20, 30, or maybe 50 functions there. So you need to write down that function, what is the use of it, otherwise you forget. Okay, so again, MATLAB itself have many built-in function, which is common. Okay, but also we need to build our own function there based on our specific system. So this is how you do it. I think based on my experience, I think this one will help when you're cataloging it like this one. So in future, like if you forget, you go back to this table and see which function I'm supposed to use here. Okay, so that's just an advice on it based on the experience. Now, we look again at that's the first function. Hopefully there's no problem with that. Okay, so we move on to the second function. So second function, that will be to calculate the number of grain in a pellet. Again, why we need to calculate the number of grain in a pellet, that one can be used later on for the surface area and a few other things. So so here we can how to calculate the number of grain in the pellet. Again, I didn't write the equation here, but I do have what they call the ready-made function for that. Okay, this is the ready-made function for this one. Okay, function again, I just indicate as NOG. That is the output name, number of grain in a pellet. So just name it like this. So this is the input that I need in order to calculate the NOG. I need the pellet, okay, the pellet radius. Again, you write it down here so that you remember. But for today, you can skip this one. You just write this part only straight away. Okay. Later you can go back to this note. Anyway, this note is given to you, so you can refer it to here. Okay. So now what we need here, we need a volume of pellet. Also, we need to calculate the volume of the grain. Okay, based on that, we can actually calculate the number of grain. Okay, the number of grain inside one pellet. So again, what is this one? This is the voidage factor of the pellet. Okay, everything need to be written there so that we remember what it is. And then also in the pellet there, when you have an oxygen carrier pellet, you also have a support material. You have to have a support material to increase the stability of the oxygen carrier. So one of the support material that we can use for iron oxide is the magnesium aluminate, magnesium MgAl2O4. So that support material also occupies certain volume inside the pellet. So therefore, we need to have a fraction of volume allocated for the support material. So this is VFS. Okay. So that's what it means. Support material of pellet volume. Okay, support material, I think fraction. Fraction. Okay, fraction there. So that's more clear. So a fraction of that volume occupied by the support material, we call that VFS. Okay. You write it down. I think you just have in line here that we need this one, this, this, and this. And then you just put the right end there, just indicate the end of this function. Okay, the line number 1, line number 11, line number 13, number 16, and number 19, and the last one. Okay, the rest you can omit it. Later you can refer back to the note. Okay, give you 2 minutes to do that. After that, we can copy this. Copy this one, right? Then we go back to our live script just now. Go back to the live script. We can test this one using the command window, but again, it's a bit hassle there. I think for this case, we just use the live script to do that rather than using the command window. So I go to my live script just now. Live script, which is this one. Okay. So what we can do is that if you want to insert a space here, right? So what we can do, we can insert the text, what they call it, session breaks or text or something like that. So here you can write again the next for function, right? Testing function number 2. Okay. So now you want to insert again the code. So you just what they call this one is code. Just click on this one, code. It will give you back that. Now here we notice that we need a few inputs here, which are not yet available here. So what we do is that we're going to type that input on the top first. So RP. So RP here, let's say we use half centimeter in terms of radius. So half centimeter of radius. So that is a 0.00 right? Or 5 E minus 3. So this one in terms of meter. Put that one meter. Again, grain radius, you can make it small, but let's say we start with a 0.1 millimeter, but it could be much smaller than that. So let's say 1 E minus 4. So that's a 0.1 millimeter, right? So this one put in terms of meter as well. Then let's say the fraction, voidage factors for the pellet. Normally pellet is very porous. So let's say we start with 0.4 there. 40% is empty. So it could be more than that. So there's no unit for this one. Then let's say a fraction occupied by the solid material. So let's say the 30%, so that is 0.3, right? So the remaining 0.3 is occupied by the oxide itself, oxygen carrier material itself. Now, actually, we can run this one. All of these are already specified. We can run it. Just click on this one, Live Editor, and click on Run. So it tells you here the number of grain is 37,500. That's the number of grain in one pellet. Okay, so there is working. It's not red there. If anything red or red alert, mean to say there's an error inside your function. Maybe there's a typos. The typos can cause an error as well. Okay, that is number one. Okay, we use this later. So move on again to, let's say we're done with that. We move on to the next one. Okay. Again, you can write something here, the note, but I don't have, uh, so I don't write that one. Just move on to the script itself. Next one is function number 3. Let's say grain mole. This is to calculate the number of mole of a grain type, any type, because we have 3 different type of grains inside a pellet: Fe2O3, Fe3O4, and FeO. So we want to calculate the number of mole of each of the grain type, right? So we use this function to do that. Okay. So that's why we write this function. So we call that number 3 grain mole. So I have it here. Again, this is what the script look like. Okay, you can copy that one. So what you need to do is that when you have the script, you can go back to the new script there. Okay, this one. Go to the new script. So they give you can type a function there and so on and so forth. So by the way, also this I don't write it, I don't want to rewrite that. I think so. What I'm going to do is that I'll show you what I have written. So you try to copy it. Yeah, this is what we have written. This one. So number and grade. Again, the name is up to you. Normally, I use a name which is quite easy to recall. Remember. Okay. So this is the function name. So there is the name of the output that you want to calculate the mole of grain type. Okay. So here I indicate that it's a millimole because the grain is very small, right? And the pellet is very small. If you use a mole, the value is very small. So I just use a millimole there for pellet. Okay. And then, of course, there's a number of grain. So here we need the number of grain for each of the type. Okay, if we know the number of grain for each of the type, so we should be able to calculate the mole of that grain. So that's why NOG here is the number of grain 1, number of grain 2, number of grain 3. RG is the grain radius. Yeah. So skip all the comment. I think you need to write this part. Number 11. Okay, that is the densities of the grain. Okay, that is from the articles, okay, from the open source. This one you need to write, and then you need to write the molecular weight for each for different type of grain, and then based on that, the calculation look like this one. So in this case, right, the calculation is multiplied with 1,000 to indicate this one because the original value is in terms of mole, but then the value is very small, so you just amplify it 1,000 times so that it become a millimoles. So 1,000 here because I want to convert the thing to millimole. Yeah. Okay, you try first, maybe 3 minutes to do that and see, and then you can test it later. Then once you do that, we just need to put it in the vector form. So ng grade here is a vector. Okay, rather than a single value, it's a vector consisting of 3 values: ng1, ng2, and ng3. Okay. All right. So I think you can use the file there. I think there's the file already. You can check with the host. I think you can supply with a file for this one. Okay, now to this, we just copy this, copy, okay, and we go find our script just now. But I think we can go to this one here, and then we can talk all in editor. Click this one. Okay, no, it's not this one. Because this one all in the MATLAB here. I think we can use this one also if you want to, but this one is the screen is a bit small, right? So this one no. So we can try to talk this and talk. Okay, now everything is here already collected here. Okay. So this one MLX. MLX indicate the live script. M indicate the normal script. MLX is for the live script. So let's say we use this one. So let's say we insert a new space there for writing something. So insert text. So testing function number 3, right? Yeah, I can do that. Then again, we insert code. So notice that we need a few input there. We haven't got this input yet. RG is already here. Okay, we can use this RG, but NOG1, NOG2, we haven't got it yet. The only thing we have a total number of grain inside the panel. This is a total number of grain. So let's assume now 70%. Let's assume maybe 70% is Fe2O3. 25% is Fe3O4. And maybe the remaining 25% for FeO. Okay, in terms of this number, right? 70% is actually Fe2O3. Let's say now we can write it as like this. NOG1 equal to 0.75 NOG. Okay, NOG is total number of grains. NOG2 equal to 0.25 star NOG NOG3 equal to 0.05 star NOG. Now we can run that here because all of the input here already specified. RG already specified the top there. We don't need to change that. So we can run this again. Live editor, click run. Then you can see here, this is in terms of millimole, yeah. So the value here is 3.79 millimole of Fe2O3, 0.888 millimole for the Fe3O4, 0.62 millimole for the FeO, according to the specification, like this one here. So we can save that. All right, so there's number 3. We can go next one, slightly more. So we go to the surface. We want to calculate the surface, the surface area of the grain. Okay, function number 4 is to calculate the total grain surface of a given grain type. Any type could be Fe2O3, could be FeO, could be Fe3O4. So this one unit in meter square per pellet. We can write that. So this is a function that already returns. So you can follow that function. Again, what you do is that you go to this one, then you can add more there. You can add more script, right? So yeah, MLX. We don't want MLX. So basically, we have we want to use a normal script. If it doesn't give you that, so what we do is that we can go to new one, click this one, script. Then after that, you can type the function so and so, right? Then after that, you save it. Make sure the name of the function is the same as the name of the file. Okay, I don't want to create that anymore. So I just show you what I already created there, number 4. So this is to calculate the grain surface. I think you just follow it first, okay? You don't need to worry too much about that. NG1, NG2, NG3 here is the number of mole for that particular grain inside the pellet. So in fact, we already calculated this one here. So what you see here, this is NG1, NG2, NG3, okay? So we already calculate that. So now based on that, we want to calculate the surface area for the different type of grain. So we use this function again to do that. Again, we still need to know the densities there. We need to know the molecular weight. And then we need to know that after that we can calculate the total grain surface area for each type of the grain. And after that we send that value using a vector. I call that vector SG grain that consists of 3 values, the SG1, SG2, SG3. Okay. So we vectorize it in it. Then like type N. Again, this is okay. You try it first. I think if you have it, you can test it, the function whether it works or not. Again, using the live script just now. So the reason why we don't want to write the whole, I think we can combine all of that function together, but it will be too long and difficult to troubleshoot it in case you have a typos, right? Normally we can have a typos there, and then that will produce an error. If the function is too long or the script is too long, it's difficult for us to detect the typos. So what we do is that we create a function according to the task. Okay, so that we have a short script. If there's any typos, very easy for us to detect it. So that is the purpose of this one. So we develop the small chunks there, and then later we can use all of that. The function here, the function that we write here, we can use it repeatedly in different file as well, or in different program. Okay, the shorter the better. Easy to detect the mistake. Because when you write something, it's very easy to to write a typos there. Sometimes wrong values could be wrong sign, could be wrong name of that variable. All of that can create the error. Okay, now let's try this one. Okay, copy this and we go back to the workshop testing MLX just now. Okay, let us insert again the space there. We got text testing function number 4. Then after that, we insert back code. Then we check first whether we already have this or not. We have RG, and this one already available to us, but the name are different, right? NG1, NG2, NG3. So what we're going to do is that, so this one is actually calculating NG1, NG2. So what we can do, we can just write like this one, NG1 equal to, we get N, sorry, N green 1. Okay. NG2 equal to N green 2. Because this SG grade have 3 things here, right? You can see here, number 1, number 2, number 3. So number 1 is for the hematite, number 2 is for magnetite, number 3 is for the FeO. NG3 equal to N green number 3. Now we already have that thing there, so now we can run it. Okay, it should be okay. Run it and produce the value there. Okay. So that is the surface area of the grain in terms of meter square. Okay. Total surface area. Okay. Now the problem here, this is a millimole, right? So we need to convert this back to a mole. So millimole, because this one gives us in terms of millimole here. So what we do here, we can type this one millimole there per pellet. So we need to convert back to a mole. So how to do that? We divide this one by 1000. So that give a mole. So that this one give us mole here. Okay. Mole per pellet, this is what we want. Okay. So again, divided by 1000 here. Divided by 1000. Now after that, you run it again, it give you something like this one here. Yeah. Okay. So this one again in terms of meter square, this one. So how do you know that? Again, you check again the file. That's why in the file, it's important that we include the unit here. What you need is a meter square per pellet, you see. Yeah. Okay. So now all of this has to be in grain of mole. So the unit of this supposed to be must be in mole. Right? Mole. Mole per pellet. Yeah, I forget to write the unit here. Supposed to be mole per pellet. Suppose that what you have is in terms of millimole, so you have to convert it back to mole per pellet. This one is mole per pellet. Okay, so that is for the number 4. We have a few more to go. So next, we use a function again to calculate the diffusion flux. Okay, I click this one, so you can just copy it. Again, this one is quite short. Again, for the time being, we just use any value for D1, D2, we just expect it to test it. Yeah. D1 is the diffusion coefficient. Again, everything is mentioned there. Okay, you can type the active line is only number 13 and number 14, right? And number 16, just 4 lines. This, this, and this one. Of course, that's to indicate the end of the function. Okay, this one is to indicate the function definitions. The function calculation actually J1 and J2. And then this one is to vectorize it so that you can export it out as a J1, J2. So J flux here contain two values. One is for J1, the other one is for J2. So very simple one anyway. But again, always write sufficient note in your script so that you know what is the function name. Very important here is the what they call the unit. The unit of variables must be included in the description of the node. And then what is the function? The unit here is important because this one can cause a lot of problem. You can produce a wrong values there, right? If your unit are wrong or not consistent. So that's why you need to include a unit in your notes. Okay. So CP here is the pellet concentration for the gas 1 for CO, gas number 2 to indicate CO2. All right, so let's try this one, whether we can try this or not. Okay. Copy. We can go back to workshop testing. If you have done that, I think we can test it. Okay, just forget first, drop down the node, just write the active line only, include the active line. All right, so I think I can increase the size of this one, make sure first the text. I can use to make it bigger there. This one can be bigger, right? Testing. Yeah. Normal testing. Okay, headings, type headings there. There's a lot of things that you can change it. Sorry. Hmm. So next, we are going to test for the function number 5, right? Insert again the text. Okay, function testing function number 5. Okay, then insert the code there. This one we can go back there and make it heading number yeah, like that. So we check whether we have enough or not. We need to insert CB value there. D1, D2, all of this we need it. So what we do is that we're going to insert value first. CB is a vector, right? Consists of two values. So we write that the first one should be the concentration of CO. So let's say put 10 there, 10 mole per meter cube. The other one maybe 2 mole per meter cube. Any value just to test whether this thing work or not. And then CP here is the pellet concentration of that. Okay, first one, maybe you put 5. Next one, we can put around 3, something like that. Any value. Yeah. Next, we can also write D1 diffusion coefficient, right? Maybe 1E minus 8. Okay, any value just to test it whether it's working or not. This one is maybe 5E minus 9, something like that. Okay, now we can test this one whether it works or not. Okay. So we try that, run it. Yeah, it works. So there's a flux, yeah. So this flux actually in terms of mole, right? In terms of mole, this one. Mole per meter square of the pellet. Mole per meter square per second per pellet. Because this one only for one pellet only. Okay. So that is once we know it's working, so we move on to the next one. You can move on to the next one, which is the to calculate the pellet number. Okay, this is the number of pellets right inside the reactor zone because that one also appear in our ODE later. So we need to prepare first the function for that one. Number 6, pellet number. Calculate the number of pellets in the reactor section given the sectional length, radius, and voidage factor. Okay. So this is the function that we prepare. You can follow very short this one. You can follow that. Okay. Yeah. Editing just okay. Pellet numbers. So we have a few active line. This ones and this and the 3 active line only to do that. So let us try whether this one working or not. So we can try test it again. Function number 6 be here. test this one, insert text. Okay, testing function number 6. Live editor, go to normal, edit. Okay. Text, we haven't got this input, right? IP, haven't got IP not yet. If we haven't got the things on the top here, so we need to specify it first. So let me specify the length of the session, reactor session. So we need to, let's say the length here maybe 0.25 meters, say. Okay, meters. Unit into meter. Radius of the reactor. Let's say we assume in total. Okay, although we have many pipes, right? So we can just lump them together and see a single reactor. So this one may be 0.5 meter, say. Meter. And then VFR, we haven't specified yet. This is the voidage factor for the reactor. So this one is, maybe we put at 0.4, 0.45 maybe, like that. Yeah. Because the reactor is fairly loose, right, in terms of packing. Then RP is the pellet. I think we have a pellet. Pellet. Which one is it? Yeah, we have this one already. RP is the pellet radius, right? So we don't need it anymore. So we don't need this. So we can proceed now with that. So we proceed. Click here. Okay, there's no red. So no red means to say the function is working well. So the number of pellet here is 200,000 something. 200 and 6,250 number of pellet, 200,000, 6,250 pellet inside this reactor zone or reactor section that we consider. You can adjust the length here. Can depend on you how what is the length type. I think it's up to you. You can make it smaller or larger. It's up to you. So now we know it's working well. So we can move on to the next one. Now this one also important. Okay, the pellet density. You know the pellet density will change with time depending on the different grain composition inside the pellet. So when the grain composition inside a pellet changes, so basically the pellet density also will change. So this is number 7 to calculate the pellet densities. Okay. There's a bit more description there. Again, you can find that one from the slide. You follow it from the slide. This one. Okay. So raw pellet, density of the pellet. So we have few active line there without a comment. These are the without a comment are active lines. So this is the one we have. Okay. So here we need to know the number of mole for each grain type inside a pellet. We need to know the pellet radius and the support material. Okay, the pellet support material. VFS, this is the volume occupied by support material. In this case, I assume that we use magnesium aluminate. This is the support material. The support material here is used to stabilize the OC so that it become more resistant to attritions, right? There are a few things there because you need to hold together all of that iron ore inside that pellet. So we need something that is a bit strong so that it give you the what they call the OC have enough sufficient thermal stability as well as mechanical stability. So one of the support material that can be used is magnesium aluminum oxide. So we need to know the density of that MgAl2O4. Density is about this one. Again, the unit here is gram per meter cube. So this is 3.58 times 10 to the power 6. Okay, gram meter cube. The rest of the molecular weight, I think, for the green. Okay. Then after that, we can calculate the mass of the support material. Okay, we need to know the mass of the grain number one, mass for the grain number two, mass for the grain number three. Then we add together. Again, actually, there's a mass of gas also that you want to consider, but I think the mass of gas is very small compared to the mass of the solid. So we just ignore it. Assume it's approximately zero compared to the mass of the solid. So the mass of the gas here does not really affect the average pellet densities. After that, you have the mass of the thing, the total pellet mass. Then from there, you can get the density of the pellet, which is the total mass of the pellet divided by the volume of the pellets. So that gives the average density for the pellets. Yeah. So let us try this one. Copy. So text testing function number 7. So we already have our RP, NG1, NG2, NG3. We already have that from here. See, this one are together. There's blue here. And then VFS, have we got that somewhere on the top there? VFS. Yeah, we have it already. 0.30% of the pellet is occupied by the support material. So we can run this one, run it, and then we get the answer. Should we get the answer for that? So that is a average density 1.0756 times 10 to the power 6 gram per meter cube. So that is average density. Next, we also need to calculate more things. There's also some more things to calculate. Is the equilibrium constant. Remember that we have the reaction kinetic like this. So this one is actually a function of temperature, the equilibrium constant here. So one function that we can use to describe the equilibrium constant is using this equation, okay, using the exponential equation like this one. So for that, let's say we create again another function to calculate just for Km. There are two Km, right? Because we have two reaction 1 and 2, so we need to have two of that, Km1 and Km2. So that's what is here. I think you can say that here, the function like constant T as a function of T. So we need to convert that T to absolute temperature, 273.15 plus T. Okay, so that becomes absolute temperature. Then for this again from the article, I can't remember from which article is that. Because this is from my student previously working in this area. So A1 is a 6 point something. Based on that, you substitute inside in the equation and you get the Km1. So after that, we just vectorize it so that we get Km1 and Km2. And within this Km is a vector. Km is a vector, consists of two values, Km1 and Km2. Okay, nearly there already. So this is a function, actual function already written there. We can test it, make sure there's no error, so we test it, right? If there's error, we need to say maybe there's a typos there. Okay, copy. Okay, let's insert again and then the text there. Okay, testing function number 8. Okay, let's try this one. Checks T. Have we supplied T yet? This one is a reaction temperature. So we supply here, let's say T equal to, I think maybe it's already here, right? I mean, we can use this temperature here, this one. So we don't need to supply that. Yeah. If you want to supply it at different temperature, yeah, you can. You can type T2, for example, right? T2 equal to 890 degrees Celsius, for example. Okay. So now we need to change this one to T2. Let's change this one. And we can run that, produce a value there. So that is equilibrium constant. No red means to say good news. Okay, no type errors. So function number 8, then we can move on to testing function number 9. Okay, number 9 a bit testing. Okay. So number 9, this one. So again, it's here already written here. Function number 9. So I call it Rx, calculate reaction rate. The unit is given in terms of mole per meter square per second. Again, this is for the pellet, is again for single pellet, this one. So we have two reaction 1, reaction 2. Cp is the pellet concentration for the gas, pellet gas concentration, mole per meter cube. Now let's say we have the activation energy given by this one, that these are activation energies. So for this, we need to call the function that we create before. So calling function to calculate reaction equilibrium constant. So we already have this function, right? So this function is already created before. So we call that. So this is equilibrium constant. They will give a value mole per meter cube. So now we have the equation. This is our kinetic equation K1, K2. So we can calculate that. Okay, reaction 1, reaction 2. Then after that, we can calculate reaction rate in terms of mole meter square per second. Actually, per pellet, but I don't want to write a pellet there because we are dealing with a pellet anyway. Otherwise, it's too long. Actually, this is per pellet as well. So R1 is given by this. Okay, we have CP1. Okay, for the because the CP consists of two values there. Number 1 is for the CO. Number 2 is for the CO2. KM1 for the reaction number 1, KM2 for reaction number 2. Yeah. Then after that, we factorize it again. Rx equal to R1 and R2. So we need to say we keep these two values within a single vector Rx. All right, now we can test it. So this one require input the concentration of the gas in the pellet and the temperature of the pellet. Hmm. We do it step by step. They're not long, so they're easy to troubleshoot in case anything there's a problem with it. So let us move on to that. Okay, this is the one, right, that we have created. So after you write it, so you need to test whether it works or not. So let us copy this one. Then we move on to the next one. So I think testing function bed control T. So now, do we have a CP already? I think there is a blue. We need to say we have the CP somewhere on top there. This one. P, do we have P? So there's a blue. You check then which one I have a blue there. There's somewhere related to this one. But if you want to use a different temperature, well, we also can use T2 there. But let's say we just use normal temperature T. So now we don't need to supply any more input to this one because all of this already specified on the top there. Unless you want to use a different value, then you can type it here. Okay. So there is value there, read there. Okay, read. So now we are dealing with the second part. Remember in this part we have this equation. Let me go back there for a while. Okay. Now we need this one. We need to have what they call this one function to deal with this logic. Okay, we need a function. Now we already create the function for this one. Now we need to add a function to create this logic. Okay. So that's what is the use for the function number 10. We call it number 10 forward backward reaction. Okay. So this one just follow exactly as what we have here, the logic. Okay. For example, right? If the reaction number 1 is greater or equal to 0, therefore forward reaction equal to this. So you multiply straight with the grade number 1 and the backward reaction is 0. If that is negative, so forward reaction is 0. So backward reaction is non-zero, basically negative here. Then you multiply with the grade number 2. Okay. Grade number 1, grade number 2. Same thing also. Then after that you end this logic. Create again next one for reaction number 2. If the rate of that is greater than 0, we use this one. Multiply by grain surface area, SG. SG grain 2 is this for the magnetite one, Fe3O4. Otherwise, it's a reverse reaction multiply with the grain surface area for FeO. Okay, then after that we create again the vector there for our forward reaction and the vector for the backward reaction. Then we call this IF forward, RB for backward, and just call it like this one. Yeah, nearly there already, nearly finished. Okay, so there is a now number 10, right? So let us test this one. If you already have it with you, so you can test it together, whether it works or not. So just copy this one. Go back to that. Okay. Function number 10. After that, we try it. Just check the value here. I think it's already specified. That's why you put a blue there. So we already have value for all of this. So we need to say we can run it because all of this already specified. Unless you want to change, if you want to change the value also, okay, you just type it again on the top here. This part. But let's say we don't change it, just use because you want to test it. So the forward reaction is all positive, you see. Backward reaction is 0. Now, let's say we use a CP2. Let's say I use a CP2 here, it's different. Let's say now uh, the carbon monoxide concentration is 0.5 because already being used, right? And then you expect the concentration of the CO2 increase maybe by 2, for example. So now for this, you type here CP2. Let's see what happens. Now you have backward reaction. You see, forward reaction number 1, number 2 here, you can easily have a backward reaction there. Therefore, when the concentration of the carbon monoxide is small, and of course the accumulation of carbon dioxide there, so we need to say carbon dioxide concentration will be larger, significantly larger than CO, so you can have a backward reaction. Yes, so the function is working. No error on that. Next, we move on to the model itself. Okay. Hopefully, we already have the function. Now we look at the model. Okay, this is the model for the pellet solid one. So we use the first three equations that we list down here. So we have a list, we have an equation here, right? This one. Uh, for this, maybe we just use this one. Too many already. So I open the function file there. You just look at what I already written. Pellet solid number 11. Yeah, this one. Okay. So the x here, this is the differential one. Tilde here, normally there's t. Okay, this is time there. But normally they will give you an error because this t is not used. But you still can run this one actually. But indicate as this one is not used at all in this particular script. So what you can do is that you can just fix it. Then just click fix it. So they just indicate as a tilde. Meaning to say this one is not used, they will indicate as tilde. So X is the state. This one is your input, the one you need to specify, right, in order to perform this calculation. So this is ODE type now. No longer this function is ODE type, not algebraic function. Before the algebraic function, this one is ODE. So from this, we need to declare the state. Okay, how do you describe your system? You have three states there, right? The state is based on the grain type. You have three grain type there. So you can see from this, the one in the end here, the NG1, the NG2, the NG3, right? This is the state one. NG1, NG2, NG3 are the state. Meaning to say the output that you want to calculate. Okay. Output, that one is directly inside the dynamic, the ODE. Because the output can be two, right? One is in the ODE one, the other one is in the algebraic equation. So the state here is the one in the algebraic equation. It's output, but it's in the algebraic equation. So we just classify it as a state. Meanwhile, the output, like the previous one, like this is also the output. If you look at this one, this output, but we don't consider that as a state. Okay. The state is the one inside the ODE one on the left hand side of it. Okay, that's the state. Okay, we have a state there. Okay, just again, we just include all of the notation there, what it mean. Okay, I think you have this, you can test it later, yeah? Then here we need to call a function before. We need to call that function for forward and backward reaction. We call it. Okay, make sure we have this one. It's available. NG1, NG2 here again. It's from there. NG3 from there. RG is directly from the input that you specify. CP is from the input. P is again from the input there. Okay, these three things is from the state itself. So that's fine. After that, you can write the model for solid for the pellet. Uh, they say this is typos, but that typos is not an issue because it's not executed. It's just not what they call the node. And so here again, I want this to be expressed as a function of millimole. Okay, this is a millimole because if I use a mole, right, it's too small. So I just increase it by so that the figure increase anyway. But for this, we scale it by 1,000 so that it become a millimole here. So I mean to say now it's expressed in millimole rather than mole. So you multiply all of that rate in terms of as 1,000. Okay. This one you don't need to because this one right already in millimole, assuming in the millimole in millimole. But this one not because these two here in terms of mole to convert that into millimole we multiply with 1,000. So, yeah. Same thing for this one as well. After that, the last part here, we vectorize again, and the x is in terms of this one. So here you use a semicolon to do that. Okay, semicolon rather than comma. Okay, so that this one is in terms of the what they call it. If you use a comma, I think it will give you an error. Okay, so this is the model. Now, in order to use this model in the Simulink method, we need to have another script to link this model to the Simulink environment. So that's why you need to have an S function. The S function, again, this one is already written there. You don't need to worry about that, including the S function here. So again, this one is level one. You can change it to level two. There's a what they call template. You can go to the math work and go there. Then basically, you can find a template to change level one to level two. But currently, I use level one because it's a convenient for me to use it. Okay. So in this case, we just need to change certain things there. So what you need to edit in this case are the following. Basically, this template is consistent. Whatever process that you have, right? You just need to change some of the information on this template. Also, if you use the level two, also you need to change some things there. Again, you have a fixed template. You can change something. But I prefer this one. It's more convenient, but it says obsolete. Even though it's obsolete, you still can use it. It just generate what they call yellow alert to indicate that you should. It's advisable for you to update it. But here I just use this one because it's easy to use. Okay, so you go to this one. Now, so what you need to do in this case, you don't need to change this one. You just need to change its name. Okay, make sure the name of this one is the same as the name as is the file name, and the function name must be the same. Okay, and then this one is a standard one, TXU flags, right? This is the standard one. You don't change that one. The only thing you change is this one. This one to indicate the steady state value. Now remember that you have three states, right? Each of the state must have a steady state value. So you just indicate as a notation x1s, x2s, x3s. Okay. So this one you need to change, the name need to change. The other one is the number of state. Okay, here we assume the number of state is three, and then number of output could be four or five. But let's say for simplicity, we assume the state, all of the state are actually output. So therefore, you have three output, three state. But in some cases, also you can actually make some calculation, like based on the state here. Therefore, the number of output can be larger than number of state. But in this case, I just specify exactly the same. The number of input, okay, before you fill in this one, okay, you need to do first, you change this part first, case number one. Okay, this system, this one you need to change, you see. So this one actually obtained from this one. Then you copy this part, right? Copy this, and then you just paste it here. Now, based on that, this is your input. Okay, you just specify the NPF, input number one, U1, NOP, that is the number of pallet as input number two. Okay, RG, again, my one is the same, yeah? Okay, same order. This one, the order of this is the same as in this one. UG, then P, same as this one. Now, CP here is a vector itself. So you indicate this one as a vector. You have two values actually. CP is a vector consisting of two values. One is CP1, right? The other one is CP2. CP1 is for the concentration of CO in the pellet. CP2 is the concentration of CO2 in the pellet. So you just continue with U4, U5, U6. And anti-IMC is a vector. You have three types of grain there, Fe2O3, Fe3O4, FeO. Okay. So basically from this, so you know, right, how the total number of input on line. Okay. Now, you just need to change this part only. The rest of this, you don't need to do anything. Okay. This one don't need to do anything. System equal to X. Because why? Your output, right? Your output is exactly the same as your input. But let's say, suppose that you want to have some output here that you want to calculate. So you have to type something here. But that one will be subject of different methods. Up to this point, it's okay. I think you just assume that the output and the state are the same. Now, this one you don't need to change it. Don't bother with this one. Just keep it as they are. Now, this one is like a bridge. If you want to use the model, this is your model. You want to use the model in the MATLAB Simulink. Okay, you need to have a bridge for that one. So this one become a bridge. Okay. Okay, and then after that, what you can do is that you go to the Simulink. Okay, maybe I just go once you reach this point, right? You already have the bridge there, so you go to new. You go to Simulink model. Click this one. Yeah. Again, you already have the Simulink model developed there. You can use that one. So long that your version is not older than mine. If your version is older than mine, let's say 2023, for example, you can open it. But if your version is 2024 B or later, means you say 2025 or 2026, you can always open it. Okay. Now let's say to create, just give a short demo for this one. Okay. Okay, we use a blank Simulink. Just for this one, yeah. Later, the other one, I think we can just use it as it is. Yeah. So in the blank Simulink, you go to library. Okay, just click this part here. Library. So you click the Simulink, then you go all down, all the way to user-defined function. Okay, there's a lot of things that you can use. So there are two types of S function there. One is level 1, the other one is level 2. Like a level 1, they're more advanced. They can accommodate more different type of information there. So we just use level 1. This is what we use now. Okay, this is a simple one, but there's a level 2 also. You check here, there's a level 2. Function filters. There are a few things. So you use this one. So you just click there. Check there. So in this case, we just call this function. So the function that we call is the S function one. Go back to this one just now. This is what we call. Okay. Just call this name on this, not everything. Just copy this one. Then after that, we have an initial value there. So actually our initial value are 3, right? If you look here, there are 3 possible initial value for this one. Again, we don't need to get an exact initial value. We just need to just rough estimation. Later it will converge and tell you what is the exact initial value. Then you can update that. For the time being, we can just have a wild guess. You should be able to converge anyway, because this file is quite small. But if you use a very big chunks of Simulink file, so most probably you can, if you don't provide the exact value for the initial value, you will not be able to converge. You will produce error there. Okay, but for this one, it's okay, small one. That's why we prefer small one, so that we don't need to bother to calculate the exact initial value, and yet it still can converge. Okay, so we got 3, right? So what we need to do now, we just put some value there. Maybe the first one is okay. We use this value as a wild case. This one. There's a value just now that we just calculate. NG grain, right? This one. Uh, yeah, this one. 3.79, 0.88, 0.62. Okay, we use that value. 3.7. This one is millimole, right? 3.79 millimole. 0.88. It's lagging a bit here. Why don't I just go and get it from here straight away? Okay, just copy this one. Copy selection. Okay. Apply. Okay. We create an input here. So to create an input on this side, what we need is the what do you call this one? Signal routing. We go to signal routings and then we create the input. This one. Yeah. Connect to this one. In the signal routing, you go to mux, MUX, mux. Okay. Then how many channels that we need? We look at the S function again. We check the S function. How many channels? Although you have 9, right? But not all of them are single value. Some of them are vector. So we just need the number of rows. 1, 2, 3, 4, 5, 6. Okay, we need 6 channel here. Channel, double click 6. Okay. Okay, we have 6 there. You can make it bigger. That's up to you. Now, I don't want to go through further. Then I show you what I have done there. A bit faster, I think. Okay, this is what we have. Okay, this is the 6, right? Then you get this one. This one is the source. The source normally we use a step, but you see, the best one. Because this allows us to change the value here. Okay, step, step, step. And then this one is actually different value. We have a sub value basically inside the box there. We have 2 channels, right? Inside this box, CP1, CP2. Okay. So let's say in this case, if you're still let's say we use this one. Okay, we want to create it here, so we need to go to source. Okay, go to source, source. Okay, okay, source, right. But thing you again, if it's a single value, we just put it there and then put a name there, whatever name that you want. And then here you can put a initial value. Okay, what is the initial value? What is the final value? In the beginning, we just make sure these are the same. Okay, they are the same. So in fact, that's what we can see here in this file that I already created. So you can see here number of pallet row, right? This is number of pallet flow per second. Let's say we put 100 here. This one also put 100. Okay, this is they call it baseline value. We have baseline value 100. Initially, we just keep it the same for both initial and final. Later, we can change the final value if you want. And then the number of pallet there, again, we put 200,000 there based on our calculation just now, 200,000, 206,000 something, like just put 200,000 there. So this is our baseline value. Okay. And the same thing also for RG. Our baseline value is 0.1 millimeter. Okay, this one 0.1 millimeter. Make sure initial equal to final. Okay. Same thing for T. T 800 degrees Celsius, right? This is a temperature. Because this is isothermal. Okay, so we assume the temperature constant throughout the reactor. Now CP here, we can create that we need 2 of that. For example, now we just copy this one, press Control and then drag it down. Press your Control, drag it down, and we'll copy it again. Press Control, and drag it down. You need 2 of that, right? So we need to have another. This is for create CP. We need to have another marks function box. Max blocks. Where is the max block just now? This one. Okay. Okay. After that, you can just highlight this one, right? Highlight and then right hand click, create subsystem. Okay, they create subsystem for you. So after that, if you want to go inside, you just double click it. And then after that, you can edit this one here. That's how you do it. Okay, I just explain for this part. Okay. So all of these are sub function or sub blocks, subsystem they call it. Same thing also, this is subsystem consists of three source here. This 1, 2, 3, three source. Because this one that what being said here, this is a vector of three quantities. Okay. So that's it. And then for the outlet, basically you can get this again from the signal routing just now. For signal routing is here, right? Check again. Signal routing. Uh, Signal routing for this one, you use a demarks here. Just click this one. No, not this one. To get out, you just click this part. Yeah. Yeah. To scale it, you just click this one. To take this out, put there. How many output do you have? You have three. So double click on this and change the number of output. Three. Okay. I think most of you know that already. Then you can connect this one. Now to view what is leaving this one, you go to sync. Go to sync. This one. We can use scope to do that. And normally use scope. And after that you put it here. Okay. Okay, that is explain the whole lot here. Okay. Then after that you can now name it so that you know what it is. Now how about this one? You want to save this data, right? So you use the workspace there so that you can send this data to the workspace, and then after that you can save it. Or you can use file as well if you want to, but I prefer to use this one. So where do you get this one? I show you from here. So again, that is from the sync again. You go to this one, workspace. Space, this one. Put it here, right? Yeah. Now here, no, normally they indicate as the name of briefcase. There's a briefcase and the whole thing, right? Contain the briefcase contain many variables there. You just call it out. If you want to change this one, so that you make it explicit like this one, right? This one is explicit name XG. So what you need to do is that you need to go to the modeling part here. There's a model setting. Okay. So let us try that one. So now I want to make it explicit. Yeah. So you go to modeling setting, modeling, go to model setting, double click, just click on this. Okay, solver here first. Normally I prefer the solver. Okay, you change the solver, it's important. Normally they use 4.5 or the 4.5 is standard one, but for our case it's slightly more stiff. Stiff problem, we use ODE 1.5S, or if there is a moderately stiff, we can use this one, ODE 2.3S. But I prefer to use this one. So you choose that. And then after that, you can change the relative tolerance, make it more accurate. So make this one smaller. I think normally my standard one is 10 power minus 6. Okay, then after that, you go to the other thing that you need to change is algorithm, make it additive. From non-additive, change it to additive one. Okay, so that's for this. And then after that, for this data import export, you click here. Normally time we can keep that one output. I think we want to save that by using the workspace just now, right? So we just uncheck this so that we don't need to do it a few times. This one can be unchecked. Yeah, this is the one that they give you the briefcase thing out, you see. So uncheck this box, uncheck it. Then after that, you can apply this one. Apply. Okay. Now it's no longer, this is simple. So the next thing what you need to do is you change the name here. Double click on this. Click. So let's call that one XV, right? Or you can use any name you want. Solid, something like that. Okay. And then the save format use array rather than time series. This one is the standard one. Time series is the default. So you change it to array. Use array structure. Okay, array. change the name and then array, then after that you click OK. Okay, something like that. So in this case, I already prepared for that. You can use that one. I just use name xg. Suppose that you run this one, right? If you run this, you will find xg returns there. Okay. You check this one, the xg is it available here on the workspace or not? Xg should be right. Where's xg? This one, yeah, xg. Okay, this one is just a soft warning. It doesn't matter that you don't need to change the level 2. Once you get your program running well, you can update it to level 2. Okay, the moment we just make it because it's convenient to use level 1. So this is just soft warning. It doesn't mean that your simulation is wrong. Okay. Right now, you can clear this one. The command window type CLC there. If you want to plot this one, you also can plot it. Plot, we have a T already, right? The T is already available, the time, the T out, I think indicate as T out. Okay, just find T, this one, the same, right? So let's say we want to plot T out versus train number 1, XG. So for all time, you can use that one. Yeah. So enter, so you can plot this one. So actually that one changed a lot, very fast. This is 1000 seconds. So maybe you want to run it a shorter time, I think. Use a shorter time. Be just 50 seconds only. Because this is just a pellet. Dealing with a pellet is a very fast one, multi-scale. The slow one is the buck rate, the slow one. Okay, so plot again. Okay, this is the actual steady state value, the one you see here. Okay, this is actual steady state value. This is just a guess one, you see. Even though you guess, it still can trace the actual steady state value. Okay. If the number of the E is a lot more and then your equation is a lot more complex, so this one might not converge. It's still to say that the derivative is a complex number, meaning to say you cannot solve it. So that's why I prefer to use a small program first, so easy to converge. So now if you want to update the initial value, you type like this one. Get D equal to length, no, N equal to length of length of the out, right? So 136 point, data point. So we want to get a steady state value. Maybe we just type SG. This one, and yeah, type that. So that is your steady state value. So once you get it, you just copy this one, copy this, copy, and then after that, you insert it back there. Okay. This is just a gimmick value, not yet the correct one, right? So we just copy and change that one. Copy and paste it. Yeah. Then apply. Now, if you run this one, so what you get a steady state value there. That means it should be a straight line, right? Okay, and this one is very small value. It's okay. You don't need to bother with that. Okay. Now, let's say now everything is correct already. The steady state value correspond to your nominal value. Again, this is a very small change. We don't need to bother with that. Now, let's say we want to change the flow rate. Okay, let me change the flow rate here. Maybe to plus 20, right? Plus 20 more. Maybe plus 20 more. Increase it plus 20. Now let's say I start at time equal to 10 seconds. I change it on. Uh, okay, you run this thing. Okay, I click. See, this is steady state, right? So this one increases. We need to say more or less correct. If you still not happy, you still can change a steady state value, but I think this one is okay already. You look at the okay increase. Okay, this one also. This one will be slower. This one is slowest one. This one is ration. You need a longer time period. This one maybe 200 seconds maybe. Okay, 200 seconds. You can see again it's still I think this is slowest ration. This part. The other two are faster one compared to this one. So you can increase the simulation time, and then after that you can actually see when it settles. Okay, you can always update this one, okay, using your own simulator there to get the initial steady state value. So again, all of these things are the same. You follow the same procedure for the other one. So again, you create again a model, right, for the pilot void. This is what we have. I just show it here without writing, okay? The same thing. So all of these things are based on the equation that you have written before. This equation. Okay, this one is for number 4 and number 5. Now on top here, basically, if you look at what we have on top here, basically some of the node, okay, some of them you need to specify again because the diffusion coefficient there is sent as a vector. There are two value inside is df. So you split it first into d1, d2, so that you can use this function. Okay, this is a calling function for diffusion flux. Again, you can name this with different name if you want to. You can call it by using different name. But this one must be the same, yeah. The name of that function must be the same. But what you want to label the output? If you want to label the output using different name, that's up to you. Okay. Now this one I use absolute. This is the trick. Because when the concentration is very small, it can be negative, and then kind of comes to diffusion flux there. So now they can make the calculation even more. So it drives you at a different solution. But although you have a solution, the solution is not practical anyway. So what you need to do is you type absolute there. This is to change this value into absolute value. Even though this is slightly negative, it's still treated as a positive. So then, just to ensure that the solution will not drift far away, it will not drift into what they call it impractical solution. Because the problem here is that these mathematical models are non-linear. So when you have a non-linear model, you can have a different answer to or different solution. Some of the solutions are not practical, but still a solution in terms of math of it. But in terms of real world, it's not a solution because we cannot realize it in practice. So we want to make sure the solution that are actually relevant to the practical world. So that's why we need to put all sorts of tricks there possible. Make sure it will not drift into a non-practical solution. Okay, that's a trick. Okay. And then you're calling at a function also for the backward and forward one. This is what we create before. Then after that, we can just write this equation. This equation is based on this one. Yeah. Okay. Then after that, we create again another bridge for that. Okay, this is the bridge for that. S function is a bridge. Okay, we update this one here. Then we update the input. Then we just call the name of that function just now. Yeah, then that's it. Then we create again one more function to test that whether it work or not. We create again another Simulink, something like this one. Yeah. Okay, this is the second one, right? Again, the procedure is the same as what we did before. Okay, just the same. If you run this one, again, it's not correctly initialized yet, so you can see that it isn't very fast because it's inside the panel. But again, this is the correct initial value, this one. Okay. The current initial value is wrong, so this is the correct one. So if I want to reinitialize this one, right, I need to change its value. Okay, to change its value again, I use the same thing as same procedure as before. This one is named as XV, right? So it checks in the workspace, is it XV available or not? Yeah, it's there. So I want to get the last value of it and equal to length T. So now XV. at time equal to n for all value of that, double dot, then you get this is the actual initial value. Copy this one. So this one is really mole per no mole per meter cube. This one the value. So now you put it there. Okay. If you run this, okay. So again, this is still changing, slightly changing because I think this one we need a bit longer time, maybe 100. See what happens here. It's still changing a bit. Again, this one changing depends on the diffusion. The in the reaction engineering, we have three types of reaction. Either if you involve heterogeneous reaction, either is a diffusion limiter, reaction limiter, or balance one. So this curve that you see depend on the value of your diffusion that you use here. If that is very small value, meaning to say the overall thing is limited by the diffusion rate. If the diffusion is larger than the reaction rate, then it's become limited by the reaction rate. Or it could be both playing affecting the dynamic of the reactions. Okay, so this one you can play around, then you can see the effect of the diffusions there. But then this one is not yet complete, you see, because we just haven't combined this thing yet. So normally it works, so it's okay. We don't need to bother too much. What we want to do is just to make sure this Simulink can work. Later we combine it. So I'm going to show you how to combine it now. This is the thing, step 3. But then we don't have that much time. I think we still can go on for the 20 minutes. I think 20 minutes to show you how you combine this together to form a bigger, what they call the entire reactors. Okay. So let me show you for the last one, which is the bulk reactor. It's a bulk reactor, right? Again, the same thing. We need to write first the S function for that. The procedure is the same as before. Now, we have 3 components there. So we're going to combine these components together. Okay, let's see first. Let's say we run this one. Okay. Okay, this is the actual value, correct value. So let's say we initialize that one. Initialize, put it here. So this one is steady state. So you have a steady, what they call stable steady state. So they will reach a new steady state once you change the input. So this one name is XP, right? That's what I named it. So let's call it XP. Okay. So copy this one. Okay. So again, this one is very small change only. Let's say we test this one, change. Let's say we want to change maybe this one, the number of pellets. Maybe we increase this pellet by maybe by 1,000. Let's see whether it has impact or not. Start at time equal to 1 second, right? Increase it by 1,000. Okay. Mm, That's too slow. Just make it a bit longer. It's a bug reactor. The dynamic of the bug is slower, very slow. Hmm. Maybe 5,000, we'll see. Yeah, this one is slow. Because we increase this one. So the things here is that we can change the value by some of the value I think need to be consistent with other parameters as well. For example, if you increase the number of pellets here, right, the volume of the reactor here should be increased as well. You cannot think because these two depend on each other, so interrelated. So how do you do that? That's why we need to calculate first the volume, and then after that we can calculate the number of pellets there. Okay, so that it will be consistent. If we change one of it, the other without changing the other, that is not consistent and give you a different value. Okay, now let's move on to. There's one thing that we can change. We can change this one, like the flow rate of this gas. Okay, let's say we change the flow rate of the gas there, inlet gas. This is meter cube per second. Maybe we increase this by 0.05 at that one. Okay, this is a bit slow. My computer is lagging here because it's sharing. Okay. Right. Okay, this one is slow process, slow dynamics. Yeah, 5,000 seconds. We can increase the length of the duration, but anyway, it doesn't show the red error there, so basically it should be fine. Okay, let's see. You can put the longer one, maybe 15,000 E3, right? 15 E3, that's 15,000. Yeah. Yes. Yeah. So this one is low, it's still increasing. Again, now, let's combine this. Okay, so we have another 15 minutes to do this. Right, this one is what we can see here. This one actually coming from the pellet, yeah, pellet void. Pellet CP is coming from the pellet component. Okay. Meanwhile, the other one, I think this one coming from the pellet. So we need to connect this one, right? Okay. So let us go to. Okay, give me another 5 minutes because my mouse battery is gone. So give me 5 minutes. Take a break first. Yeah, take a break first. For a while, yeah. 5 minute break. Okay. Okay. All right. So we create a new Simulink model. Let's see whether we can combine it and then no error. Hopefully there's no error. So I'm going to copy this one, copy this. Okay. So this is from the Sim palette solid, yeah? Copy this. Then we move on, put paste that here. Okay. Give me a space later. Then after that we copy the other one is a palette void, this one. Okay. P. Paste here. Okay, we paste already. Now we need one more. Last one is the reactor one. Copy. Okay. All right. So what we're going to do is that we're going to connect this. Which one I require CB? CB. CB coming from this one is from the panel, right? Should be from here. Yeah, should be from here. CP. See CP here. So I'm going to tap this one, this information. Tap this information and use this in this. Okay. Just remove this one first. Click here, then you can connect it there. See, click this one first, right? Okay, I click this one, and then see the blue there, I just connect it to this one. See, connected already? Yeah, start to be, yeah, now we do wiring now. You see whether it work or not. If it red, I don't know, but hopefully there's no red. Okay, it's working, I think. Because now we are, I'm sharing now online. That's why this one is slow. Okay, it should be okay. Okay, okay, there is value there. But before that, let us settle this one. Make sure it's in the nominal value now. Nominal value, nothing is changed there. Okay, change. So this one. Okay, this one change as well 100, like just back to normal nominal value there. So what we changed just now, we just bring back to nominal value. Okay. All right. So what else do we need to change here? Let's see first from this side. Which one is it? CB. Okay, CB, right? It's coming from this one, right? CB here. All right. So what I'm going to do is that I'm going to disconnect this one and connect it to here. Let's see whether it's still working or not. Okay, it's running. There's no red, so it should be okay. All right. Now what else? NG. Where NG coming from? NG coming from here. This one, right? This part. See this one. So this one I disconnect this. Just throw it back a bit. Disconnect this one. Okay, this one must be connected to this one. Uh, Try it again. Is it working? Yeah, okay. Still, there's no red there. Should be okay. So CPI space okay. And NG okay. We disconnect that. DF. Okay, this is the common one. We can connect that later. What else we have here? HIRG. Okay, this one this side. This one, right? Where this thing coming from? CP, right? It's coming from the other one. So we just disconnect this one. And then we connect this to CP. CP is this one. Connect to this one. Right. Try it again. An issue here. It's okay now, right? Still running, it's okay. Okay, this one, the thing we just bring it back this to 0.1 there. Nominal value. Okay, anything else that we need to change here? CBI. That's it. I think we already connected all of them. This is wiring. Okay. So I can change the color so that I can trace this thing where it coming from. So block for ground color, maybe use red there. Okay, this one connect to this. This one right change the color there, go to right click format, maybe for ground use blue. Okay, connected, and this one change the color of that. Use green maybe. Okay, see ya. Anything else that we need to connect? Okay, this one can remove it. It's already gone. It's okay. So no need anymore. Yeah, I think it's connected already. This one. So all of them connected. CB. Let's check for anything else that we need to change here. This one, yeah. Okay, all are connected, all three connected already. So it doesn't matter, we can make it a bit longer, maybe 6,000. 6,000, 6,000 seconds, so about 1 hour plus, right? Let's see. Yeah, like that. Zero. So the best thing, it doesn't go to negative. If it's going to negative, then you can forget it. We need to say your simulation give a impractical result. Yeah, zero only, not negative. Okay. So all of them converted to NG1. There, see this one. Okay. So basically, this one also check what happened here. Okay. So this one not still changing. This one we can make it 20,000. Yeah. So this one appear to be keep increasing here. So not yet. We need to run it first. Okay. So this one is very slow drift. This one. Okay. Okay, so increasing. Now the other thing also here, we need to look at the common inputs. Like which one is the common input? We can lump them together. So you look at this one, basically we can lump them together. There's a few steps here. Basically VFR, common. Maybe just make it bigger, this one. Make the wording bigger, right? Go to format, go to this one. Okay, which one are common so we can combine them together? Common. Okay, for example, NOP here is also used there, right? So this one, I don't need that. So I just remove this. Same thing. Remove this. Then you connect this one here. What else? The common VFR. Okay, which one is the common? RG. Here also there's some common things here, I think. Yeah, NPF. This is common with this one, right? This one. Just make it bigger a bit. So this one is common. So we just remove this. Connect this to this. Number of pallet. This is common with this. We remove this one. Then share with that. RG. RG, this is common with this. So we remove this one. There. Next T. Which one got T here? This also T, right? Common. So remove this one. T. NGI. This is the inlet one. Which one require NGI here? Okay, common. And then we look at this side here. RG. Okay, this one is common, right? Between these two. So remove this one, common with this. Remove one of that. Share with this one. Yeah. RP. Okay. Anything else we common we can share together? RP. Only one here. This one is common. RP with this one. So we'll just remove one of that. Connect with this. Yeah. PFP. CPI. Inlet. DF. RP. Yeah. That's it. We already more or less we have the things there. Basically, this one we can shrink it again if you want to shrink it. We can create subsystem on this one, right? So we can make it smaller. Okay. But I don't want to make it create a subsystem because easy to see it in this current form. Once it confirm everything's okay, then actually you can shrink it, make everything smaller. For example, we can create subsystem here so that we don't need to look all of that thing. For example, yeah. So it become more tidy. This also can create subsystem there. Yeah, here. Maybe we can try that one. You see that? Yeah. Then after that, you can arrange that. So actually it becomes smaller and smaller. Okay. This also can create subsystem here. Okay. The only thing is that this one later you need to bring it out again, some of the input, so that we create again a shell. This one again, we need a bigger shell for this one. Because currently what we have here only 3 compartments. Okay, this pallet. Okay. And then the other one is the bulk reactor. The other one is a pellet void. So all this thing, okay, just to represent one section only. But remember, for the reactor, we have a long reactor, could be 10-meter long, and this reactor only, this section only about 25 centimeter, right? Let's say you have 5 meters, therefore you need 20 of these. So for 20 of these, you need to combine them. Okay, combine them together so that it become represent the reactor that you need. Okay, this one only one section. Okay, so let's say I move on to the, because this one need a bit more time, so I will show you what it look like anyway in the case, in the one I already developed there. So I just move on to the next one. Okay, I show you first. So go to this one. Script reducers. Okay. So this one is the reducer. No, this one is the backup. This one. This one. Okay, this one just represent one section, right? This one is how it looks. Okay, this is what we have. This one is the more complete ones because a lot more calculation, so the wiring is more complex there. So this one again represent the three zone just now, three compartment, one, two, three. And this one just represent one section, but you can connect them to another section like this one. So in this case, I have a 10 section there to represent the reactor. So this reactor long, the length of this reactor is about 3.5 meter. Each of these about 0.35 meter in terms of length of the section. Okay, so I think yeah, it's a very intense, quite an intensive demonstration here. I think we cannot really finish completely as we expect it to be. But I just managed to show you up to this point only. I expect I can do more than that anyway. So now we combine 3 points. Now let's say if you want to do this to create again the section, right? So basically your inlet is this one. Okay, this is your gas inlet. Let's see whether we can, because this one need a little bit planning, to do this. So all of these have to be out there. Okay. PFP. Okay, this one just now already. Okay. This one, all of this need to be out because this one need to be specified, all of this. So you create a shell there. Yes, yes, yeah. So basically you create a shell, they look like this one. Okay, just give you an illustration first. Because I don't think I can finish all of this in 3 hours. So what we need to do is just create again a shell like this. Okay. Okay. This one need to be inside. All of the input you want to put it outside. Okay, put it outside. All of that has to be outside. This input outside, and then you arrange it again. Okay. Yeah, that's how it look like here. Yeah, yeah. All this input need to be specified. You put outside. Okay. So this is only first section, zone one. Okay, zone one or session one. So in order to get another section, you have to duplicate this one. You copy this, okay, and you paste it. Now notice that this one requires an input here as well. So you need to be careful which one is the constant input, which one is the one that should come from this one. We normally what we want to do is that we want to send some of the input from the zone number one, and then that actually become the input of zone number two. So we need to select them. Okay, those are the common one. Actually, this one is common. For example, VR here is common. This one can be taken as common. This one can be common. Okay, the inlet gas here is not a common one because one is leaving this section, right? Is FGO. The FGO has to be sent out, and that become the input here. Okay, so that should become the input for the second zone. And then RP here, this is a constant. Okay, this one is for example, this one is input input to the zone number one. So this one cannot be sent to this zone number two. To zone number two should receive CB1. Okay, so what we need to do is that we're going to take out the CB1. Which one is CB1 just now? This one, right? So what I'm going to do, I'm going to create an output there. So you go to create an output. You go to Simulink and go to the things. Get this one out. Put it here. Drag one of this here. Then we connect this to this one. Then you can say this one is CB1, right? No, we call XB1, XB1, XB, CB1. Because CB got two, just put CB there. Otherwise we get confused. So now we have one there. So this one need to send to where? You look at the number. Which number is this one going to? 1, 2, 3, 4. So this one, 1, 2, 3, 4. So going there. So this is the common one. We can insert that like that. Okay, this one can be insert like this. This one can be common connect to this because it's a common. RP again is a common, so that one can be going straight to that. CPI. Okay, CPI. The CPI cannot be this one cannot be the inlet for this is actually from the other side because they are counter current, right? If you look at this model, this is counter current model. Okay, I just go back to that one. Okay. See? Well, see is here. Gas is here. So we're actually starting here. Our zone one is starting from the gas inlet. You see? This is at the end of the reactor, OC inlet here. So CP here. So this one, the CPI is a counter current. It should be coming from this one. So what you need to do is that you get an output outlet here as well. You just make an outlet from this one. So then you can send the information from CP here out. So now you create again the output it here. Okay. B. Just name that XB XB1, right? Because it's stage number one. Yeah, stage number two. This one CB2 CP XB2. So you need to name it so that you know where it is. This one should be sent to this one. Replace this. This one you remove that. Yeah. Now we counter current. So that's why you connect this. I think the best one is probably the like what I have here. You see, you see this one. This one is interconnected, right? This one going to this counter current, and then after that you have this one going to that. Okay, some of them are common one. We just feed them together there. This one, yeah, from the other one. So there is a counter current mode anyway between the oxygen carrier and the gas one. Yeah. All right. I think that's all I think for this line. Is it okay? So I think we already passed our time. Already 5 o'clock, so 5:30 already. Okay, that's all. Going back to the first sorry, Hans, I think this is a bit too long. Cannot complete it in 3 hours. Okay, so at least I think I show you the illustration, how you connect them together. But then what you need to do is we create a script, okay, for all of the function that we need. So after that, we create the Simulink model, right, for each one of them to test, make sure it works. And then after that, we combine. Then finally, we create the section like this. And of course, for this, we don't really need to write any more script there unless you want to add a few more things. So you can still add a script into it. But basically, we are using the previous script to duplicate it. So we don't need to keep writing the script. So we can have as many zones as you like. Okay, based on this one. Yeah, that's all for now. Thank you. So it's a very long and quite tedious one.
Okay, thank you, Dr.
Okay,
Gibran.
yeah.
Actually, for the detail of it, maybe I will contact Dr. Gibran for the complete set of the maybe Simulink for the live integration.
Yeah, yeah, okay.
And
Yeah, I
thank
can give you
you.
the what they call this one of the samples from this particular exercise. Yeah, I pass it to you so that you can distribute to the participants after that.
Okay.
I prepare first and put a little bit explanation there so that to complete this workshop. Anyway, so I create a few more slides anyway for this part three. Okay.
Okay, thank you. Okay, because the time is very take a long. So
Sure.
maybe there is another question or something, you can email us
Mm.
in the I will get a chat box. Maybe you can also contact directly to Dr. Jabrun Nandung. So I think the Dr. Jabrun will be open to discussion about the detail on this design.
Yes.
Okay.
Yes.
And thank you for Dr. Jabrun for the
Yeah. Thank you. Thank
very
you for
knowledge.
organizing the workshop.
Okay,
Yeah. Thank you.
knowledge of the simulation. I
Yeah.
hope we can contact and make another workshop or webinar. So thanks you to participants can participate for this webinar for workshop. Actually, we for the next month we have also webinar for process system engineering
Mm.
topics. And if you want to grab the e-certificate, you can fill the form in the chat box, so we can arrange it. So thank you for all and good afternoon. Thanks you, Dr. Jobron, for your insight, knowledge of the workshop. Thanks you for good afternoon and assalamualaikum warahmatullah.
Okay. Bye
Thank
bye.
you
Have a
all.
good
Bye
day.
bye.
Bye bye.